Hello, everyone. Hope you are doing well. My name is Rafiei. I'm a research assistant professor at Old Dominion University. And today I'm going to present about a framework for adaptive multi-turn jailbreak attacks on large language models. So as an outline, we have an introduction and motivation, the background and the related work, and then thank you. And then I will talk about our proposed approach, that is HarmNet framework, and then experimental result, and finally the future work. So large language models have demonstrated a significant advancement in natural language processing, powerful in understanding, representation learning, and generation objectives, and widely used in dialogue systems and interactive agents. And large language model, the alignment method, although the alignment method improved the safety, but still large language models are vulnerable to different adversarial attacks. Specifically, jailbreak attacks are a critical threat. They bypass the safety mechanism and elicit harmful, biased, and illegal outputs. And why, specifically regarding multi-turn jailbreak attacks, why multi-turn jailbreak attacks are dangerous? So the multi-turn jailbreak attack is going to have a conversation with the victim LLM and try to persuade the LLM to generate unintended or legal output. So it distributes the malicious intent across benign turns, conversation turns, and evading the static filter in the guardrails of LLM. So it reveals deeper and dynamic alignment gap compared to the single turn attacks. And the existing multi-turn jailbreak attacks, just like chain of attack Crescendo from Microsoft, actor attack, MRG agent, demonstrate novel strategies and vulnerability in large language models. And we introduced HarmNet, modular model agnostic framework, include 3 main phases for multi-turn jailbreak attack. The first phase is TopNet, that aim to map the adversarial search space and enable diverse attack paths. The next step is a simulator or a sandbox that aim to refine multi-turn query chain and prune low potential branches. And the third step happens in the real world, is going to produce optimized multi-turn queries for real-world jailbreak attacks. Why our method improve over the previous state-of-the-art multi-turn jailbreak attack works? And the most factors are systematic exploration instead of narrow heuristic. And the second main reason is iterative and feedback-driven refinement and pruning for higher efficiency. And our model is, our framework is model agnostic, work on both closed source and open source models as a victim. So as a result, in terms of experimental result, our multi-turn jailbreak attack achieved 94.8% attack success rate on ChatGPT 4o. We compared to the actor attack 10% better ASR accuracy and as a closed source. And also it achieved it outperformed Crescendo by 38.4% and chain of attack with 72% on Llama model as an open source victim model. And our framework achieved better diversity across different victim models. For example, on ChatGPT 3.5, it achieved diversity score of 0.35 compared to the one of the state-of-the-art actor attack that is 0.27. So as a related work, the large language models widely adopted and deployed in sensitive domains such as education and healthcare, but it's still vulnerable to prompts that enforce the aligned large language model to generate unsafe outputs. So as a related work, there are two types of jailbreak attacks: the single-turn jailbreak attacks that can be crafted prompts, suffix optimization, few or many shot tuning, and to generate a single-turn attack, there are different techniques, just like bias exploitation, prompt decomposition or reconstruction, hierarchical attack trees, and these type of single-turn attack tend to work in low complexity and surface level, but vulnerable to context-aware defense system. So the current defense-aware system can easily detect them. But regarding the multi-turn jailbreak attack, that it will happen in a dialogue-based method between the attacker LLM and the victim LLM, and it aims to spread the intent, the malicious intent, across multiple dialogue turn, exploiting memory and escalation. And it is hard to detect because it evades the statistic filters, and the representative methods are crescendo, chain of attack, and rail yourself. Why the previous works fall down? Why the previous multi-turn jailbreak attacks fall short? Because of three main reasons. The first is most of the previous sort of works, they explore a small subspace of adversarial search space as a first main reason. The second reason is those sort of approach often rely on brittle, heuristic, or handcrafted manipulation to assemble query chain. And the third main reason will be they heavily use the fixed template, limited their diversity and adaptability of adversarial prompt. So we introduce HarmNet, including three main steps in order to create initial set of query chains. Then the second step is a simulator. Sandbox is going to do refinement, iterative refinement and pruning based on the feedbacks and try to create more harmful jailbreak attacks. And the third step is the iterative traversal. It happens in the real world, try to attack the real victim model. So our framework addresses the previous issue by semantically exploring the adversarial subspace, refining and executing multi-turn attacks through a semantic network we call HarmNet, and a feedback-driven simulator, and an adaptive traversal. So the HarmNet briefly build semantic network from the harmful goal. Consider we have a harmful goal that can be a malicious input, user input. It will extract main topics related to that harmful goal, then some sample related to topics and some real entities, and then initial query chain. Then the second step, the simulator is going to utilize to conduct refine and pruning based on harmfulness and semantic similarity metrics. And the traverser, in the real attack, it will execute the optimized chain, query chain in the real time. And the key strengths of our work is our work aimed to explore a comprehensive adversarial search space via HarmNet, our first module, and then a simulator tried to refine and prune the initial query chain. And finally, the traversal will execute in a real time to optimize the refined multi-turn query chain to do adversarial jailbreak attack. Okay, the first module of our work, HarmNet, or network of thought. This is the first module of our framework. The HarmNet built a structured semantic graph that scoped the adversarial search space for an input goal. Consider we have an input user prompt that is adversarial, that is malicious. So our method will try to expand the input the user malicious input into topics, samples, entities, and finally initial query chain. So HarmNet will produce a diverse set of topics, main topics related to the input goal or user malicious, input user malicious with some constraint. At first, the topics should not overlap to each other. And also the correlation between different topics with the main goal should satisfy one specific threshold. After extracting main topics, the next step is for each topic, the HarmNet generates samples where each sample refers to a small entity set. We have a category, a category of real entity set, and each sample can refer to a small set of entity set. And the one constraint we have in here, each sample semantic similarity with the input goal should be higher than one specific threshold, otherwise it prunes. And after generating the samples, for each sample that is correlated to to a small set of entity, the HarmNet will produce short multi-turn chain, the initial multi-turn chain regarding one entity, samples, and topic. As you can see here, we have the main goal, that is the user in malicious input. Based on that, thank you. As you can see here, for the initial, for the input user malicious input queue, HarmNet will generate several main topics related to that main goal, and for each topic, it will generate different sample where each sample is related to a small set of real entities. For each entities, the HarmNet will generate an initial query chain that we will it will pass to the next step, to the next phase. In the second module is a feedback-driven simulation, a simulator. In here, this is the 5 minutes. This is one of our novelties, our paper novelties. It's going to simulate the real world. In here, we have attacker, we have a victim model, we have a evaluator. So the initial query goes through the victim model, it generates the initial response, and then our simulator will check if that is unknown response that is not available in the real world, that is hallucination detection, and we will prune it. Otherwise, it will go through the judge model. In the judge model, it will verify it. It will assign one harmfulness score from 1 to 5, when the 5 is less harmful and 5 is more harmful. And then it will go through two main filters, harmful refinement and semantic refinement. So the harmful refinement will be the current harmful score minus the average of the previous harmful score for each query in the query chain. If that is less than one specific threshold, it will be pruned, and also it will calculate the semantic similarity of the current query in the query chain, and it will calculate this equation, the current semantic similarity minus the previous semantic similarity related to the previous query. If that is less than a specific threshold, it will prune it. Otherwise, it will go to read if these two constraints is not satisfied, it will go to the rewriting step. It will rewrite the query, and again, it will go through the victim model. And this iterative refinement will happen until a specific threshold, and then finally, if it satisfies the semantic and harmful refinement, we save it as an optimized query chain. Otherwise, we will our framework will prune it. And the network traverser, this is a real world. In here, we have the attacker model and the real victim model. And for each query chain from the previous step, it will iteratively go through the victim model, then get the response, and the response goes through the judge model. Then if it achieve if it get rejected, that is the harmful score is low, it will go through the query rewriting. Otherwise, if it got the most harmful score, that is 5, it will save as a successful jailbreak attack. So in terms of experimental setup, we utilize two different benchmarks, that is HarmNet and advanced bench, and various metrics that are attack success rate, diversity of strategies, harmfulness distribution, and compute and latency metrics. And as a victim model, we consider the open source and closed source. The open source can be ChatGPT 3.5, ChatGPT 4o, Cloud 3.5, and the open source method will be Gamma, Llama, and Mistral. And we also use ChatGPT 4o as an attacker and the judge model in the real world. And for the simulator, we integrate 3 open source LLM in the simulator. And the baseline model for comparison is single-turn, just like GCG pairs, and code attack, and multi-turn method, just like crescendo chain of attack and actor attack. As you can see, as a first experimental result, our method achieved the best attack success rate among different jailbreak attacks through the open source and closed source victim models. The second series of experiments try to evaluate based on the diversity score, the diversity of different paths toward designing different diverse jailbreak attack. In here, as you can see, our method HarmNet achieved a better diversity score across different open source and closed source victim models compared to the other SOTA jailbreak attacks. And in terms of statistical analysis, our method achieve low average time per query chain in the real-time jailbreak attack with low number of API call and low number of query to do a successful jailbreak attack. And as an application study, we investigate several hyperparameters. The first is the number of iteration in the simulator. As you can see, the number of iteration in the real world, in the traverses, as you can see, if the number of iteration increase, then the attack success rate increase. But from number 5 to 10 and 15, the attack success rate is reduced. So we select number 5 as the number of iteration in the real world to do refinement. And we also consider remove the first module, HarmNet, and remove the second module, simulator, and then calculate the attack success rate. As you can see, when the harmful has its own module, all of the module, it will get the highest attack success rate. And finally, the final series of experiments is utilizing some initial guardrails. Consider the llamas or Mistral or open source LLMs has the guardrails. But if we want to add the defense-aware guardrails against different adversarial attack, our method HarmNet will achieve the higher attack success rate against those defense-aware mitigation compared to the two other SOTA jailbreak attacks. And finally, as a future work, we aim to extend the HarmNet framework. We aim to integrate the HarmNet with the defense agent trained via reinforcement learning from AI feedback in the simulator, and then simulate adversary defense interaction to evolve both sides dynamically, and finally develop an adaptive detection system that anticipates evolving jailbreak attacks. And the second future work can be how to extend the HarmNet to include chain of thought or reasoning-based jailbreak attack, evaluating how ThoughtNet plus traverses the second and third module adapt when the target model expose or simulate intermediate reasoning. And the last future work can be cognitive, how to extend our ThoughtNet first module to include psychological and emotional layer, simulating how human attackers build trust and trust-based attacks. And thank you so much.
I think we have about a minute or two for questions, and Raina will help run the mic a little bit. So Raina, I think your first assignment is to go run all the way to the end.
You mentioned an attack success rate. So that's a yes or no, I guess, question. Can you go into a little bit more detail on how you measured that? Attack success rate percentage. Can you explain a little more how you evaluated that?
Thank you so much. We have an evaluator, a judge model that assigns harmfulness score from 1 to 5. The number 5 is most harmful, and we consider it as a successful jailbreak attack. So for the input benchmark, just like HarmNet, that include, for example, 174 malicious user intent, if for each of them, one of the jailbreak attacks from our HarmNet achieved number 5 score as a harmfulness at the real-time attack, that will be the successful jailbreak attack. The others that achieve harmfulness score from 1 to 4, we will consider it as an unsuccessful jailbreak attack. Then we can easily calculate the attack success rate between the successful jailbreak attack with harmful score 5 and the other unsuccessful one.
Hi, folks. Sagar had to step out for a call. I'm Ethan Rudd. I'm your program chair. Let's take a couple more questions.
Great presentation. My question deals with your future work. You were considering how to deal with the reasoning models. Have you considered the fact that you can control and compress the context window? So if I think about from an attacker's perspective, I know you're going to compress the context. So when I give you the first time you compress, and when you compress the second time, the two combined causes a bypass.
Which one of the which one of the future work you mean? I present 3 future work.
Your number 2 item on future work that you wanted to go to dealt with looking at the reasoning models for bypass, and I'm going, does that include looking at when you compress the context window?
Yeah, actually, we believe that there is a great opportunity in order to investigate the victim model chain of thought. Because the cutting agent LLMs, just like GPT-01, they generate chain of thought. Based on the investigation of different steps in chain of thought, there are some capability or opportunity to find some potential way to attack to the victim model based on, right now in our model, we are only utilizing the judge model feedback based on the response, but we believe that along with the response, we can also evaluate the chain of thought output of the victim LLM to find new vulnerabilities and extend more efficient jailbreak attack based on those intermediate levels of chain of thought from the victim model. Thank you.
Cool. Let's move on to one more question. In the back.
Awesome. Thank you for the presentation. So 2 quick questions. The first one is, I think on your table, you had shown that you were using GPT 2.5, GPT 4.0, Claude 3.5. I was wondering if you had tried some other models as well, like the larger models, like GPT-5, DeepSeek, etc. And then my second question is, when you use Crescendo, what implementation did you use? I'm very curious to see how you set things up as well. Thank you.
Regarding the Crescendo model, you mean?
Yes, so the Crescendo attack, right? So I'm not sure if you implemented your own version of Crescendo, if you were using some publicly available implementations of it, because that can also have an effect on how well it performs.
They have an implementation in their Pilot framework. We find it, and based on that Pilot implementation, we generate some multi-turn jailbreak attack, and we also consider the similar configuration for all of them in the same environment to get a fair comparison. And most of the SOTA work attack, just like Crescendo, most of them has pre-attack and in-attack. And we add a simulator at the middle as a booster to improve their efficiency. And another issue with Crescendo that achieve low ASR is it only consider a narrow subspace of adversarial space. In our work, the first module, the network of thought or ThoughtNet, tried to investigate the adversarial space as a ThoughtNet, different type, different paths that ends with the query chain. That is the second reason that our method could outperform SOTA method, just like Crescendo or Actor attack. Thank you.